Hi, my name is Jiwon Seo, and I'm an assistant professor at Hanyang University, Korea. I'm happy to present our work, Parallel and Failure Atomic Cuckoo Filter for Non-Volatile Memories. This work is done in collaboration with two of my master students, Hyungjun and Bonggi, and Professor Hee-jin Park at Hanyang University, and Dr. Chang-dae Kim at ETRI. This is the talk outline, and I will start with NVMs and approximate membership query data structures. Non-volatile memories such as 3D X-Point have high performance, persistency, and byte addressability. These characteristics of NVMs give opportunities and also challenges to system softwares. Particularly much work has been done on persistent index data structures like bpros3 and hash tables. Approximate membership query data structures, or AMQs, are often used in index data structures. AMQs approximately store a set of values to answer membership queries. They provide these APIs to insert a key and look up if a key is in the set. Some AMQs allow delete inserted keys. Because they are approximate data structures, AMQs have small false positives. That is, lookup X may return true even when X is not previously inserted. These AMQs are hard to optimize for NVM because first, NVMs are fast but still 2 to 3 times slower than DRAM, so running DRAM version of AMQs will be very slow on NVMs. Second, AMQ operations are cheap, consisting of only a handful of computations, so we cannot use complicated optimization. For example, existing work on SSD-optimized AMQs do not work on NVMs because their techniques are often too complicated. Now I'm going to describe Cuckoo filter because it is a good candidate for a fast AMQ for NVM. Cuckoo filter stores a fingerprint or a short hash over key. And it has buckets and slots like this one, and typically a bucket has 4 slots, each storing 12-bit fingerprint. For insertion and lookup, it uses 2 hash functions to find the designated buckets. For insertion, we use the hash to find the bucket and store the fingerprint in an empty slot like this one. This insertion does not need an eviction. As opposed to this insertion here, the 2 buckets for H1 and H2 are full. Then we select a slot to evict and store the fingerprint of X in the evicted slot. Now we need to insert the evicted fingerprint. This eviction makes Cuckoo filter slow in high load factor when most buckets are full. For lookup, we examine the 2 buckets specified by the 2 hashes. And if any of the fingerprints matches, it returns true. Here we may have a small false positives. Conventional Cuckoo filter has 2 issues on NVM. One is its eviction overhead, which already exists in DRAM but becomes more substantial in NVM. The other is failure atomicity. Because standard Cuckoo filter uses 12-bit fingerprint and 4 slots per bucket, a bucket is 6 bytes in size. So the bucket size is not the same as NVM's atomic write unit, which is 8 byte. As shown here, updating a bucket may span across 8-byte boundaries, and thus the update may not be done atomically. So if the system crashes while updating a bucket, Cuckoo filter may be in an inconsistent state. To solve these issues in Cuckoo filter, we propose AniFilter. First, we use these 3 optimizations to improve its performance on NVM. Second, we use logging to ensure consistency in case of system failures. Let me first go over these optimization techniques. Spillable buckets allow spilling a fingerprint in the bucket's neighboring buckets. When inserting a key, if the bucket denoted by H1 or H2 is full, we examine next 2 buckets. If their first slot is empty, we store the fingerprint in that slot. For example, here, because the bucket denoted by H1 is full, we examine the next bucket, and because its first slot is empty, we spill the fingerprint there. Then we encode the fact that the first slot stores a spilled fingerprint in the bucket. If the second slot's fingerprint is larger, then it means that the spilled fingerprint is in the first slot. Spillable buckets reduces eviction by spilling a fingerprint in a nearby bucket that is likely to be in the cache. To study the effect of spillable buckets, we compute the eviction probability at a given load vector with and without spillable buckets. For that, we design a probabilistic model that computes the probability that a bucket has k number of keys. The details, including proofs, are in the paper, and we present the result of the analysis here. This graph shows the eviction probability of Cuckoo filter and AniFilter computed by our model and the actual experimental result. The two plots are very close with less than 2% point error. It also shows that the eviction probability for AniFilter with spillable buckets are lower than the eviction probability of Cuckoo filter. Our next optimization is look-ahead eviction. This optimization selects the fingerprint to evict that does not incur further eviction. For that, it stores a single bit per bucket that represents the occupancy information of the bucket. If the bucket is full, the bit is set to 1, and otherwise it is set to 0. Instead of random eviction, look-ahead eviction examines occupancy flag of each fingerprint's alternate bucket and evict the one whose alternate bucket is not full. Note that this occupancy flag is stored in DRAM because it can be reconstructed from the filter when a failure occurs. Bucket primacy is an optimization for lookups. We categorize buckets for a key as primary and secondary bucket. When inserting a key, we attempt to store it in the primary bucket specified by H1. If that bucket is full, we have to store it in the secondary bucket specified by H2. In that case, we say that the primary bucket is overflown, and we encode this information in the order of fingerprints here. Later in lookup, if the primary bucket is not overflown, we do not need to access the secondary bucket, thereby saving NVM bandwidth. Now let me discuss logging. For logging, we categorize buckets into three types, A, B, and C, based on the position of 8-byte boundaries in the bucket. They need different number of logging. For example, type A buckets need no logging for new insertion and one log record for inserting an evicted key. Here we give an example of logging for type B buckets. For more details, please read our paper. We use 8-byte log record to store bucket index, fingerprint to insert, and fingerprint to evict, and other information. When we insert a new key, as in this example, we log bucket index, fingerprint to insert, fingerprint to evict, and unaligned fingerprint fragment, and other information of the bucket. With this log record, we recover if a failure occurs. To recover, we check log record to read FPI, fingerprint to insert, FPE, fingerprint to evict, and bucket. Then we test if FPI and FPE are in the bucket. For these three cases, the update is incomplete, so we undo and reapply the update. For case D, we need to further examine other information in the log record to determine the completeness of the update. I'm going to give an example recovery for case D in the next slide. When we insert a key into this bucket, we first write a log record and update the smaller 16 bits like this. And before you update the rest, if a system crash occurs like this, we need to recover from this inconsistency. Although FPI is in the bucket and FPE is not, the update is not complete. A completed update is shown on the right for comparison. In this case, we examine the metadata in the log record. Specifically, we examine the speed encoding here. Because the speed encoding in the log record is different from the speed encoding in the bucket, we know that the update is incomplete. The logic behind this is described in the paper, so for the details, please read our paper. Now we undo the update using the data in the log record, and then we reapply the update. So far, I described the sequential AniFilter, and its parallel version is slightly different in these 2 points, synchronization and logging. Parallel version needs synchronization, so we use lock. We assign a single lock to 4 buckets like this. For both insertion and lookup, we hold 2 locks for primary and secondary buckets to prevent deadlock. And we apply lock ordering for holding the 2 locks. For spill buckets, we use try lock, and if we fail to acquire the lock, we give up spilling. Although this scheme ensures deadlock never occurs, live lock may occur. First between an insertion and multiple lookups, and second between multiple insertions. For the first one here, we make the locks for lookups to have bounded wait time and retry acquiring the locks. For the second one, live lock between multiple insertions, the probability of this is extremely low, lower than memory bit error rate. So we simply ignore this. Again, the details are in the paper. For logging, we need each thread to have its own log entries. Moreover, we need to make each thread to write an explicit commit mark in the log so that we can determine write order between two threads accessing the same bucket. Now let me show how we evaluate AniFilter on NVM. We use Intel Optane DC persistent memory as well as Quartz emulation for the evaluation. We evaluate AniFilter and 4 other filters: Cuckoo filter, Morton filter, rank and select quotient filter, and Bloom filter. To the best of our knowledge, these are all state-of-the-art approximate filters. First, we evaluate parallel throughput of Cuckoo filter and AniFilter for insertion, successful lookup, and uniform random lookups. X-axis is load factor and Y-axis is million operations per second. Line graph shows the throughput and the bar graph shows latency. You can see that AniFilter shows much higher performance for insertion, and also for lookups, AniFilter is 10% faster on average. This is because NVM's limited bandwidth, and AniFilter requires much smaller bandwidth than Cuckoo filter. For sequential throughput, we compare the 5 filters here. AniFilter and Cuckoo filter shows much higher performance than the other 3 filters, and that's why we only compare Cuckoo filter and AniFilter for parallel performance. Compared to parallel insertion, for sequential insertion, Cuckoo filter's performance is close to AniFilter, but for sequential evaluation, only a fraction of NVM's bandwidth is used, and thus Cuckoo filter's performance is not limited by the bandwidth. And that is similar for lookups as well. We also evaluate the 5 filters with varying read-write latencies emulated by Quartz. In all latencies, AniFilter shows higher performance than other filters. Now we separately measure the effect of lookahead eviction. We measure the throughput with and without lookahead eviction. We also run the experiment with occupancy flags reduced to half so that 2 consecutive buckets share a single occupancy bit. Here you can see that with only half the size of occupancy flags, the throughput improvement is substantial. We also evaluate the synergy between the 3 optimizations. Specifically, we measure the effect of spillable buckets and lookahead eviction on bucket primacy. Here it shows the percentage of non-overflown buckets for each load vector. You can see that the percentage of non-overflown bucket increases as we apply spillable bucket and then apply lookahead eviction. The higher this percentage is, the faster the lookup is in AniFilter, because for these ones, we only need to access primary buckets. Let me conclude. We proposed AniFilter on optimized Cuckoo filter for NVM. We designed these 3 optimizations to improve the performance of AniFilter. We use minimum logging to ensure failure atomicity. When evaluated on Intel Optane DC PM and Quartz emulation, AniFilter shows substantially higher throughput than other state-of-the-art AMQs.